we want to review some key points you need to know before you start working on part 2 of this two-part assignment where we want to build a motion model for speeding up motion. Let's get started. In the previous lab, we discovered that the position equation for an object speeding up from rest at an origin will be in the form of future position equals some constant of proportionality times t squared. Okay, that's what is k? K is this constant of proportionality. Remember that, just as a little aside here, the graphs that you graphed showed initially that, position is proportional to t squared. Well, to turn that into an equation, we have to have some constant in front of the t squared, and so that's what we call the k. It's just, maybe I think it comes from German, because the German word for constant is Konstant. Who knows? This proportionality constant k, next bullet, is this proportionality constant k in the equation above likely relates to an object's rate of speeding up. Speeding up rapidly probably means big, a bigger constant of proportionality. Speeding up gradually probably, we're not totally sure, but probably means a smaller constant of proportionality. Okay, so we're going to be using the letter K for this constant in front of the t squared. If a position versus time graph is nonlinear, like the one shown here, the velocity of an object at some instant in time, that's instantaneous velocity, is equal to the slope of tangent line to the point of the curve at that time. Oh boy, I think an example would help. Slope of tangent line at point on curve at time t. All right, let's do an example. Let's suppose that I'm interested in getting the velocity on this graph here, the velocity at something around like just after 2 seconds, so like right here. Well, I'm going to find my point on the curve. I'm going to take out my straight edge, which I'm not doing right now, but I'm going to try to, and I'm going to draw a line that touches, doesn't cross the curve at that point. At least in theory, mathematically, it intersects at just one point. All right. That's how we get instantaneous velocity. The slope of this is instantaneous velocity. The blank of a velocity versus time graph quantifies the slope of a velocity versus time graph quantifies the rate of speeding up. For example, in the graph here, to the right, the slope of the velocity versus time graph to the right is, okay, let's look at the slope. The slope is rise over run. Okay, so slope equals, I see a rise of 10 meters per second, and there's a run of 4 seconds, so that's going to be 2.5 meters per second. I'm not worried about sig figs. For example, so there we go, 2.5 meters per second. This means the object's velocity is changing by 2.5 meters per second each second this plays out. All right, now we can let's get to the word, because you already know the word. Humans have invented a word for the slope of the velocity versus time graph. For this, we have a word. We don't want to always say slope of a velocity versus time graph or rate of change of velocity. That word is acceleration. and we abbreviate it with lowercase a. Always lowercase, never uppercase. Since last point, since acceleration is defined as the slope of a velocity versus time graph, and slope is rise over run. I'm not even sure. Whatever. Rise over run. Here we go. The definition of acceleration is, right and big, acceleration is going to be the change in velocity divided by the time interval. Now, this is average velocity, but I don't want to dwell on that. It's just, right now, it's velocity. Okay? Sorry, I mean, average acceleration. All right, there's the notes on what you should know before starting with this assignment.